Welcome to Biochemistry 412, the Biochemistry Lab. This course will be a hands-on approach to more about what you learned about in Biochemistry 410 and 411. I'm your instructor, Dr. Ayers. There's my contact information. The Canvas course website has the contact information for me as well as all of the TAs. This includes their office hours, rooms where they are, etc. You may come to anyone's office hours or make an appointment if you can't fit in. In this course, we will teach you the theory and principles of a lot of biochemical techniques, ranging from electrophoresis to chromatography, biochemical assays, biochemical calculations. There are a lot of calculations in biochemistry. We will work on how to analyze and interpret your experimental data. We will use a lot of common lab equipment and learn more about how to keep a lab notebook. What you need for this course is the lab manual that's available at the MSC bookstore, a bound composition notebook with lines to serve as your notebook, knowing that Canvas has your grades, lectures, etc., and that all quizzes and exams are on the computer with lockdown browser, so bring your laptop to class. The grade breakdown is 30% worksheets. Note that the worksheets are designed to talk you through your experiments and your results. We'll help you with the worksheets. You'll get 2 tries. So most people get all A's on the worksheets. This will be offset by 30% for quizzes and 40% for your final exam. You'll get to drop the lowest quiz grade. If there are any discrepancies in posted grades or questions about the grading, let the TAs know within 1 week of their posting on Canvas. We will not change grades more than a week after posting. Let's talk about your lab notebook. It's a record of what you did and why. It must be clear enough to repeat the experiments in 5 years. Many of them are complex and need notes, and even sometimes for yesterday or last week, you won't remember everything you did in detail. The quizzes at the beginning of most class periods are designed to make sure that you've prepared for class. So these will include pre-lab questions, for example, the procedures that you'll be doing. As we move on through the semester, it will include questions from previous labs and worksheets, the results that you might have gotten in other experiments. And note that the quizzes and the final exam are open notebook. You may write in your notebook whatever you want and use these on your quizzes and final exam. The notebook will start for the next class period. For your notebook, you want to have a cover and title page. Put your name on the cover. You don't want to lose your notebook and not have it available for your exam and quizzes. Title page including your name, class and section number, your phone number and email address, your TA's names, emails, office hours, all useful information, but make sure there's enough information that if you lost your notebook and someone else found it, you can get it back. A table of contents is optional. It can be helpful, but our inexpensive little notebooks don't have page numbers, so it's up to you. And you need to write legibly in ink in your notebook on one side of the paper only. In science, we try not to hide data, and so the ink, to make sure that you can't easily delete things. You'll never white out your data. If you have data that's bad, you'll simply draw a line through it, so it's still readable. Before you come to the class, read the lab manual and fill out, and again, handwritten in ink, not photocopied, the date the experiment was performed, the purpose of the experiment, 1 or 2 sentences with the overall reason for doing that experiment. For example, today I'm making a cell-free extract to use to purify GFP and RFP. Background, 1 or 2 paragraphs on what you're doing and why. What is your cell-free extract? What is GFP and RFP? Why are you doing this? And then the procedure in enough detail to repeat it without the lab manual. I love troubleshooting questions. A lot of the time, it's talking about the procedure and making a change in the procedure. You need to know what should be done to know if something has changed and what the outcome would be. During and after class, you'll fill in your results and your data analysis. This can include raw data, tables, calculations, etc. Do note that the worksheets talk you through most of your calculations. You might want to have those calculations in your notebook to refer to on the exam. You can attach the printed Excel graphs and gel pictures and label them appropriately. Everything else needs to be handwritten. Some days we don't have any real results, but you can simply put what you did that day. For the discussion, you discuss what your data means and any problems. Just because you get an absorbance of 0.2, 0.3, 0.4, don't leave it at that. Say what that means. Finally, a conclusion that must be supported by your data. Did you successfully purify GFP from RFP TAT? Your data should support this. Note that all the work should be in your own words, including on the worksheets. You'll answer questions and make graphs independently. You'll not simply print out 2 copies of the graph. You must have your own or you'll get half credit. If you open the drawers near you, you'll see the workstations for each pair. The drawers are numbered with your workstation. For example, 1B. That will be the drawer for the 2 people who are working together. That's a useful number to put on a lot of your samples to help you identify the samples the next week or 2. There's also a small drawer in front of you with safety glasses, so you don't have to bring your own. If you look at that shared drawer, it contains the tips that you'll need, the racks, tubes, etc., even Sharpies and scissors. In the drawer between partners, you'll see cuvettes with extra tubes and tips for you to use when you run out of tubes or tips, or if you need cuvettes. Let's cover some of the safety rules in the lab. These rules are in the lab manual. They're in the slides and they'll be posted on the board. There'll be no eating, drinking, or chewing gum in the lab. You need to have closed-toed shoes. If your hair is long, you need to have it tied back. We will give you eye protection and gloves in 5 different sizes. You can call 911 if there's an emergency. We have a fire extinguisher in the lab, a first aid kit, and an emergency stop to turn off all power and gas to the lab if needed. You'll see that there are eye washes in the sinks. There is also one that's in the hall, as well as a shower that's really just a handle in the ceiling. You pull that and it will be a shower if you have managed to get chemicals all over yourself that need to come off. We have a spill kit in the lab if you have a spill. Most of us, however, only need a few paper towels because we have relatively small quantities. There is a broken glass container that looks like the box on the slide. If you do break something, let the TAs know. You should put your backpacks and purses on hooks under the bench or just sling them under the bench. They can't be on top of the bench because it would be a safety hazard. By the door or on the computer, you can find materials safety data sheets to tell you about the chemicals that you need. And there is a safety agreement in your laboratory manual that you'll need to sign. We have 3 different types of waste containers in the lab. Regular waste, just put in the big trash cans. If you break some glass, you put it in the appropriate box. Glass only, no pipettes, no cuvettes, etc., things like that. Only glass. If you put paper towels in there, we get in trouble, so don't. We also, when we work with bacteria, etc., have a biohazard container that we'll pull out. This will be autoclaved at the end to make sure it conforms to the regulations. Note that on your bench, there is a small orange container that has a bag in it. You can use this for your waste, things like your tips, etc., as you use them. At the end of the day, you'll take that to the appropriate trash can and dump the contents, but don't throw away the plastic bag. When we start working with bacteria, we'll throw it into the contents into the biohazard trash. When we're all done with that, we'll autoclave even the bag that's in there, put out fresh bags, and we'll go back to using regular trash. Before you leave class each day, make sure you clean up, put everything away, empty your trash. We give you paper towels and cleanser to clean your bench, and let us know if anything is missing. What you're going to do today is first work on your skills. Some of you are good at pipetting, some are not. Pay attention and learn to pipette. If you want to get out of the lab faster, pipette well. I will make you stay and redo it until you get good lab results or until class period is over. If you pipette well, you'll finish sooner. We will also learn how to use our spectrophotometers using red dye 40, which is a food coloring, and so it's harmless. Your lab notebook will start next time. We'll also start our experiments next time. The worksheets are due according to the schedule on Canvas. Our spectrophotometers are great specs. They have a 6-cell holder, which holds 1 blank and 5 samples. The light beam travels left and right for the cuvette that's in front with a 1 centimeter path length. We are using semi-micro cuvettes, which means they're squished together in the bottom where the light goes through, so we don't need to use as much liquid. For Beer's law, A equals epsilon CL, we use a path length of 1 centimeter. With our semi-micro cuvettes, you need to make sure that the light beam will go through the long direction or the 1 centimeter. If you look at the cuvettes, they have an arrow that is matched by the arrow on the cuvette holder to help you match them up. If you have your cuvettes in the wrong orientation, it's roughly 0.5 centimeter, so your readings will be substantially smaller than they should, or higher, depending on what you've done. So make sure you always have it in the direction where it'll rotate into the light with a 1 centimeter path length. So the front cell, the front cuvette, is your auto zero, your blank. The light goes left to right, right to left, it doesn't matter. So that should be the direction of the long way. The next sample will rotate into place, so you want to make sure the light would go through that direction, and so on. What you'll do today is construct a standard curve with Excel using dilutions of a solution of known concentration to determine the concentration of an unknown concentration of solution. From this, you'll calculate the extinction coefficient back with our Beer's law for red dye 40. Basically, an extinction coefficient is a proportionality constant that lets you determine the concentration of a solution. You'll also have a solution of red 40 of unknown concentration that you'll use for the extinction coefficient you determine to calculate the concentration. From your known samples, the dilution series that you'll make, you'll construct a standard curve using Excel or another software program. Make sure you label your graph with your title, your axes, your units. Usually in this class, we'll use scatter plot, add a trend line. Make sure you have an equation in R squared. Note that the trend line should pass through or close to 0. If you're not getting very close to 0, you're probably not pipetting correctly. So make sure that that works well. Often we will go ahead and force our trend line through 0 so we can handle small concentrations. I think one of the hardest things to do on a graph is give it a good title. The easiest way to think about it, though, is what type of graph are you doing? If you tell me you're doing a standard curve or a Lineweaver-Burke plot, I know a lot about that graph. For instance, if you tell me Lineweaver-Burke, I know that there's a substrate, an enzyme, a product. I should have a positive y-intercept, which will give me the Vmax, 1 over Vi or Vi. A negative x-intercept, which will give me Km. And that's a lot of information from 2 words, Lineweaver-Burke. Also consider what your assay type is, if you have that substrate, product, enzyme, etc., and what's being measured. Give good information, don't simply restate axes. So let's take a look at this. Your absorbance today with the red 40 should increase linearly with increasing concentration. If you do get any outliers, you need to redo them. So on the x-axis, we actually have our concentration, but I'm leaving all the labeling up to you. On the y-axis, it'll be your absorbance, and you will also fill that out. Note that the graph is made using simple data points connected by a trend line. The data points themselves are not connected. The trend line is added to the data points. I have the equation y equals 0.01x plus 0.002. The r squared is 0.998, so the data fits the line really well. An r squared of 1 is really good. It gives you a feel for how your data is doing. What does it mean if you get a data point that is significantly higher in absorbance than you would expect? What could cause that? Well, one possibility is you have not mixed your cuvette well, and the more dense ingredients will be at the bottom, giving you a higher reading. So if you get a data point that's unexpected, make sure you go back and mix. It is a lot faster to mix and check it again than it is to redo it. How about if you get a data point that's significantly lower than expected? Remember what we talked about before? In this case, the cuvette could be in the wrong orientation, so you're not getting a path length of 1 centimeter. It's less than that, and you're reading a low concentration. It could be made accurately, but it's reading wrong because of the orientation. Easy fix here is to simply check the orientation and switch it if it's wrong, and then maybe you have a perfect line. It's also possible that your reactions are not made correctly, but it's faster to check orientation and mixing and things like that before making them again, especially once we get to 10 or 15-minute incubations. All right, take a look at this graph and think about everything that is wrong on this graph. Think about the x-axis. What should that be? Does that give you any information? Not much. You don't know what the alcohol is. You don't know what the units are. The y-axis is absorbance in nanometers. The units are not nanometers, though. Absorbance does not have units. This is making it look like the units are nanometers, but it's set at a wavelength of whatever, 340 nanometers or something like that. So this looks wrong. In the title, all they did was restate the axes, no additional information. Absorbance versus alcohol concentration does not help. Note that the data points are connected and a trend line is added. Also, at the 0 point, the trend line does not go that close to 0, so there are probably some pipetting issues in there. We have our series here, but it doesn't have our equation and r squared. So this graph is not very helpful. I can't understand that much about it. As far as I know, it could be the effect of drinking margaritas on a college student. Let's take a look at a better version of the graph. We now know that we're looking at the conversion of ethanol to acetaldehyde by alcohol dehydrogenase. And on our x-axis, we're looking at ethanol. Concentration is in millimolar. On the y-axis, we're following the absorbance of the chemical NADH being produced because we can't directly measure ethanol or acetaldehyde. And we know that the wavelength is set for 340 nanometers. There is a trend line added, but the dots are not, data points are not connected. We have our equation and our R squared. Note that a couple of the data points are not even on the line, but the R squared is 0.9989. The data is still very good. So that really helps us. Now let's go back to our Beer's law, A equals epsilon CL. What is the extinction coefficient from your graph? Do you have any idea? In our case, the extinction coefficient is, again, a proportionality constant, but it's a slope of the graph. So for our equation, y equals 0.0123x, the extinction coefficient would be 0.0123. How about the units? Can you tell what the units are? Let's go back and think about our Beer's law. So the units of absorbance, there are none. So we know that whatever units are on the right, they have to cancel out to be no units because absorbance has no units. We have our epsilon that we're trying to figure out. The C is concentration, which we know is millimolar. L is path length, which is 1 centimeter. So the epsilon has to cancel out the millimolar for C and the 1 centimeter for L. In this case, our units would be millimolar -1, centimeter -1. So our full extinction coefficient would be 0.0123 millimolar -1, centimeter -1. Final note for today, the safety. We're using red 40 or red dye 40. It's food coloring, so it can go down the drain. No particular safety requirements. You do not have to wear gloves or eye protection, but you are welcome to. And your cuvettes, once you've dumped the liquid down the sink, can go into the regular trash. We'll go ahead and get started.